Deep in the Al-Kharj desert of Saudi Arabia, summer temperatures regularly climb past 55 degrees Celsius. On this barren ground, an industrial complex manages over 200,000 purebred Holstein dairy cows. From a biological standpoint, this should be impossible. Holstein cattle evolved for temperate climates, requiring temperatures between 4 and 21 degrees Celsius. Once ambient heat crosses 25 degrees, thermal stress crashes milk production, and anything above 40 degrees causes fatal organ failure. Yet, this facility extracts an average of 42 liters of milk per cow every single day. That is nearly twice the output of standard dairy operations in Britain and Western Europe. Delivering over 3.5 billion liters of fresh milk annually, this operation supports a $5 billion commercial empire. So how do they keep these cows cool, feed them in the middle of the desert, and move millions of liters of milk from the barn to the factory every day? Let's see how the entire system works. To understand how this operation survives, we must look at the brutal hydrology of the Arabian Peninsula. The region receives less than 100 millimeters of rainfall each year, while relative humidity frequently drops below 10%. At the same time, the dry desert atmosphere evaporates water 30 times faster than precipitation can replenish it. On the surface, there is not a single permanent river or freshwater lake. The project started after the 1970s global oil crisis exposed how vulnerable the kingdom was to foreign food imports. In 1977, Saudi planners established Almarai with a single practical objective, which was to build a fully self-reliant domestic dairy supply. The primary engineering challenge was locating a massive and continuous water source. Without surface water, engineers turned downward. They conducted geological surveys and drilled between 100 and 700 meters into the bedrock to reach the Wajah and Bayad formations. These are deep fossil aquifers containing prehistoric water trapped underground for thousands of years. To bring this water to the surface, the facility operates heavy industrial submersible turbine pumps powered by 700 horsepower motors. Each production well discharges up to 6,000 liters of water per minute. This continuous volume supplies drinking systems and powers high-capacity cooling equipment. Once the water supply was secured, engineers had to solve the heat problem. Open pastures were completely out of the question, so the company built sprawling concrete barns stretching for miles across the sand. These structures use a negative pressure tunnel ventilation design. Massive industrial exhaust fans at one end pull millions of cubic feet of air through the buildings every minute. This continuous airflow prevents heat buildup and exchanges the entire volume of indoor air every few minutes. Thick insulated roofing blocks radiant solar heat from entering from above. Securing water and building insulated barns was only the foundation. The real mechanical challenge was keeping the biological engines inside them alive and producing at record levels. Inside these tunnel-ventilated structures, managing a 1,500-pound biological system requires non-stop thermal control. A high-producing dairy cow generates substantial internal heat simply by digesting food and synthesizing milk. In an environment where the outside air exceeds 50 degrees Celsius, failure to remove that heat results in immediate metabolic collapse. To solve this, the engineering relies on the physics of latent heat of vaporization. Because desert air holds less than 10% relative humidity, it has a massive capacity to absorb moisture. The facility takes advantage of this through an automated cooling cycle. Overhead high-pressure lines mist the cows with water for exactly 6 minutes, thoroughly wetting their coats down to the skin. Immediately following the spray, banks of large industrial fans blast air across their backs at high velocity for 15 minutes. As the moisture evaporates rapidly in the dry air, it strips heat directly from the animal, maintaining an effective microclimate between 21 and 26 degrees Celsius. However, external cooling solves only half the problem. Inside the cow, the rumen acts as a continuous fermentation vat, generating significant internal thermal energy. To regulate core body temperature, water extracted from the deep fossil aquifers is routed through industrial refrigeration chillers. The system brings the drinking water temperature down to between 15 and 18 degrees Celsius before pumping it into automated stainless steel troughs. Ingesting chilled water cools the internal organs directly, preventing heat-induced appetite suppression and allowing the animal to maintain high dry matter intake. Fueling this metabolic engine requires a strictly calculated diet known as total mixed ration. Industrial mixing wagons blend imported premium alfalfa hay, corn silage, soybean meal, bypass fats, and microminerals into a uniform feed. The nutritional profile is balanced specifically for net energy for lactation. The formulation delivers high energy density in fewer pounds of feed, minimizing digestive fermentation heat while providing the exact carbohydrates and amino acids needed for continuous milk synthesis. This high-density intake creates rapid milk accumulation, requiring a rigorous milking schedule. While traditional operations milk cows 2 or 3 times a day, this facility runs a 4-time daily milking protocol, once every 6 hours. More frequent milking relieves physical pressure inside the udder and triggers the sustained release of prolactin, the hormone responsible for milk production. Moving tens of thousands of animals through milking stations every few hours requires specialized infrastructure. The facility utilizes heavy-duty rapid exit milking parlors configured with 75 to 100 stalls each. Once milking is complete, the entire front retaining gate lifts pneumatically, allowing all 75 cows to clear the platform simultaneously in seconds. A single operator team can prep, attach vacuum clusters, extract milk, sanitize the teats, and release a batch of 75 cows in 5 to 7 minutes. The entire biological process is tracked through continuous data collection. Each cow wears an RFID neck transponder and an electronic leg pedometer. These digital devices measure steps to identify the precise window for artificial insemination, while also recording rumination minutes and daily movement. If a cow shows a minor drop in chewing activity, the software flags her for inspection long before any outward symptoms of illness appear. Quality control at the milking stall is completely automated. Inline conductivity sensors inside the milk claw test the electrical resistance of the milk from each quarter of the udder in real time. If the system detects elevated ionic levels indicating early-stage mastitis, an automated valve diverts that milk into a separate discard tank in fractions of a second. This mechanical precision keeps the herd infection rate under 0.5%, well below the standard 2% threshold found on traditional farms in North America and Europe. By combining thermal physics, heavy plumbing, and real-time biological telemetry, the operation transforms an extreme desert environment into a high-yield production line. Once the milk leaves the cow, a new mechanical race against time begins. Raw milk exits the udder at roughly 38 degrees Celsius, which is the prime incubation temperature for bacteria. In the desert heat, leaving raw milk uncooled for even a short period would cause rapid spoilage and destroy the entire batch. To neutralize this risk, the pipeline routes the warm milk directly from the milking claw into industrial plate heat exchangers. These stainless steel units use countercurrent flows of chilled food-grade glycol and ice water to drop the milk temperature from 38 degrees down to under 4 degrees Celsius in less than 5 seconds. This sudden thermal drop arrests bacterial reproduction instantly without altering the delicate milk proteins or butterfat structure. From the cooling plates, the milk flows into massive insulated storage silos before loading into heavy transport tankers. Every 40 minutes, around the clock, a specialized insulated tanker truck departs the desert farm clusters and heads toward the central processing plant at Kharj. These double-walled vacuum-insulated tanks prevent thermal transfer, ensuring the raw milk arrives at the processing facility at a steady 3 degrees Celsius, even when ambient highway temperatures exceed 50 degrees. At the central plant, automated machinery takes over completely. The facility processes millions of liters of raw milk every single day without human hands ever contacting the liquid. Centrifugal separators spin the milk at high speeds to separate cream from skim, allowing precise standardization of butterfat content. The liquid then passes through high-pressure homogenizers operating at thousands of pounds per square inch to shatter fat globules into microscopic droplets, creating a uniform, stable emulsion. To guarantee shelf stability across long transport distances, high-speed lines route a major portion of the volume to ultra-high temperature processing. The liquid is flash heated to 138 degrees Celsius for exactly 2 seconds and rapidly cooled back down, destroying residual bacteria while preserving natural nutrients. The finished product is then sealed into multi-layer aseptic carton packages that block both oxygen and ultraviolet light. Processing is not limited to fluid milk. To maximize profit margins, the operation converts surplus volume into high-value dairy derivatives, including fermented milk known as Laban, thick yogurts, processed cheeses, and butter. These value-added products command higher retail pricing per liter of raw milk equivalent, insulating the enterprise from raw commodity price swings. Getting these perishable products to consumers requires the largest dedicated cold chain fleet in the Middle East. The company operates more than 8,000 refrigerated trucks and delivery vans fitted with heavy diesel refrigeration units. These vehicles run continuous direct delivery routes across Saudi Arabia, the United Arab Emirates, Kuwait, Oman, Bahrain, and Qatar. This direct-to-store distribution network supplies over 110,000 individual supermarkets, grocery stores, and local shops. The entire timeline, from the moment milk is extracted from the cow in the desert to its arrival on a retail shelf thousands of miles away, takes between 24 and 48 hours. The economics of this operation prove that extreme engineering can yield substantial financial returns. The vertical integration model generates annual revenues exceeding $5.2 billion. By controlling every single variable in-house, from deep well water extraction and climate control to processing, packaging, and fleet logistics, the business cuts out third-party markups. The sheer scale of producing 3.5 billion liters of milk annually amortizes the massive initial investment in concrete, steel, and chilling equipment down to pennies per liter. Managing 200,000 cattle also creates a massive logistical byproduct, with the herd generating thousands of tons of manure every day. Automated scraper systems clear the concrete alleys continuously, funneling the raw waste into industrial separation units. The mechanical separators press the slurry, splitting it into liquid and solid fractions. The liquid runoff is routed to anaerobic settling lagoons for biological treatment, where the treated water is recycled to flush barns and cool mechanical systems. The solid fibrous material undergoes rapid thermophilic composting, where natural aerobic decomposition temperatures reach over 60 degrees Celsius to neutralize pathogens and weed seeds. This sterilized byproduct is converted into high-grade organic soil conditioner, which is deployed to stabilize surrounding sand or packaged and sold commercially across regional markets to offset operational costs. Extracting record milk volumes and delivering them fresh across an arid continent is a verified engineering triumph. However, keeping this colossal biological machine running in a water-starved desert exposes the entire system to severe geopolitical and resource vulnerabilities. To feed a herd of 200,000 cattle, the operation originally farmed over 22,000 hectares of desert using center-pivot irrigation circles. That agricultural setup consumed more than 400 million cubic meters of deep fossil groundwater every single year. Because prehistoric aquifers do not recharge, subterranean water tables dropped by several meters annually, threatening the National Strategic Reserve. In response, the Saudi government issued a strict mandate banning the domestic cultivation of water-intensive green fodder. Rather than downsizing production, the corporation initiated a global logistics maneuver known as importing virtual water. Through its agricultural subsidiary, the company acquired and leased tens of thousands of acres of farmland in the Palo Verde Valley of California, the Butler Valley of Arizona, and prime agricultural zones in Argentina. By utilizing local American water allocations and unmetered rural aquifers, they produce hundreds of thousands of tons of high-grade alfalfa hay. The harvested forage is mechanically pressed into high-density bales, packed into maritime shipping containers, and hauled over 13,000 kilometers across global shipping lanes directly to the desert feeding bays. Today, 100% of the herd roughage arrives by sea. However, this outsourcing strategy triggered substantial geopolitical friction. During severe regional droughts in the American Southwest, local communities and state regulators launched investigations into foreign agricultural pumping. This culminated in state authorities terminating public land leases and shutting down new commercial well permits in Arizona. Furthermore, maintaining an 8,000-mile ocean supply chain exposes the entire dairy operation to maritime shipping bottlenecks, canal closures, and volatile bunker fuel prices. The Almarai facility demonstrates that mechanical cooling and precision automation can conquer the most hostile climate on Earth. Yet, it also proves that extreme agriculture cannot bypass basic resource limits. It simply shifts the physical water deficit to the other side of the planet. Between long-distance resource logistics and next-generation closed-loop food systems, which model represents the true future of global agricultural security? Leave your analysis in the comments, and subscribe to the channel for more breakdowns of large-scale industrial engineering. Thank you for watching.